And it's recording again. Okay, so that's the statement of representability, and then I can spend some time on what it looks a bit like and how the proof goes.
Just
right?
to be sure, if you say for some mu, do you mean that mu should be large enough, or
No,
mu
it doesn't matter. Okay, no, this works for all nu.
Right.
Because if you take quotients of f or of f twisted with something, there is an equivalence, right? You can tensor with O of x of nu to go from f to that thing, that's tensoring with a line bundle, and that is an invertible operation. If I tensor with the minus nu line bundle, then I go back. So if I have a quotient of f after some base change, that's the same data as giving a quotient of f twisted by nu. I mean, I can twist it, and then I get a twisted quotient. If I have a q from f of t to some g, then I also get, by tensoring, over Ox of t with the Ox t, I get another quotient, and so those functors are all isomorphic actually. So it's a bit, this nu we could have taken it 0 also, and it would have been the same, the theorem would have been as strong. Yeah, and as difficult to prove. Yeah? Other questions? Yeah?
So, do you have any examples of this PS curly E, which are not projective?
The B is a locally free module of finite
PSE.
BSE.
P. Curly. No.
This thing.
No, above in the definition. There's PSE. This projective.
This thing.
Yeah, this project. Yeah.
You can
So
say
you know,
PSE itself.
Just to get a bit more familiar with the.
Yeah, well, I don't know. I'll think about it.
Okay, sure.
But the reason it is taken is that people, well, I mean, if you look at this text by Nitsure, he says all these various notions of projectivity are not equivalent among each other, and none of them is local on the base. so they're all bad in some way.
No, just for me to get a bit more acquainted with this notion.
Well, what you would need, I think, is an E that is not a quotient of OS to something. Right? Well, or even maybe twist it with a line bundle. Because if you twist this E with a line bundle, you still get the same projective bundle. Right?
Yeah.
By the same argument in a way. Yeah? Because that projective bundle, that projective bundle, if you want, is also a kind of quad scheme itself. It parameterizes locally free rank 1 quotients of E. That's like a projective space, right? It parameterizes lines or hyperplanes, and in that sense, it is also itself such a quad scheme.
Well, if you come up with some examples of
Okay, I'll think about it, but not in real time at this moment.
No.
So it says that, it doesn't say, this is just a representability theorem, right? But I said it says also, it is represented by a disjoint union of strongly projective OS schemes. So where does this decomposition come from? And I think in the examples I gave, you see a bit that it came from numerical invariance of these quotients, right? Or of the subschemes that I was parameterizing there, like degrees of divisors or dimensions. So that is paragraph 2. Decomposition by Hilbert's polynomials. Okay, so for K field, and if I have X a projective K scheme, X over K projective K scheme, with a very ample line bundle OX of 1, right? You can pull it back from some embedding of projective space, and F, a coherent OX module. What do we have? we have the Hilbert polynomial. The Hilbert polynomial, and that is why these things are called Hilbert schemes, I think. Chi of f, and this is a polynomial, say, with coefficients in Q and with a variable that we call lambda, and it, as a function, it induces a function, of course, from z to z, and well, it will, and that function takes any integer to the Euler characteristic on this space x of the sheaf twisted by n. So this is, by definition, the sum over all I of -1 to the I dimension over k of the ith cohomology group on x of this twisted sheaf. Yeah? And one knows that these are given by polynomials. And polynomials that take integers to integers do not have to be integer polynomials, right? They can be like binomial coefficients, then they have some denominators. Yeah? Okay, so now this is easy to connect to that, of course, because there is a theorem that maybe I should say, for x over s, if I now go back to the relative case, strongly projective with an OX of 1 coming from there, right? And f of finite presentation and OS flat. So these are typically the kind of things I want to parameterize, right? You can say that the function that sends a point of the base to, I would say, chi of the sheaf restricted to this, right? So here I have x over s, and if I have a point, I have here a residue field, k of s, and I can take the step of that, and I have this map, and then here, when I pull back this thing, I get the fiber over that point, and if I have here a sheaf f, then here I get the pullback sheaf that is indicated by fs, and then you can take this thing. This is a function from s to the set of. This is not at all a map of schemes, huh? Well, maybe, because actually it is, but then this is just a disjoint union of points, and then this with the discrete topology. This is locally constant. And you could say, and S is the disjoint union indexed by all polynomials here of subschemes S phi, on which this function has the value phi, right? Is that clear? That at least that you can point-wise you get a polynomial then, and actually the statement is that the set. These sets where the polynomial is the same are open, and of course then they are also closed because their complements are also open. The union of opens. Okay.
This is overall or is there?
Well, not all of them are non-empty, maybe.
Oh, okay, I see.
Right. I mean, some of these polynomials even do not take integers to integers, so that this is certainly empty. Yeah, but for this ease of notation, I'm not going to make a difference. Okay, so then you can also decompose this quad functor, right? This quad f over x over s is the disjoint union over all phi's of quad of subfunctors. F over x over s, right? You can say if my functor already gives, every object that I look at decomposes my s, then also this functor is then it will be itself a disjoint union. It's just like a Picard functor. You can say, I look at line bundles of degree 0, of degree 1, of degree 2, of degree -1. The Picard functor is a disjoint union here indexed by integers of curves then, where you can take a degree, and here you have Hilbert polynomials. Okay. So, and it is these things that are projective. These are strongly projective in that theorem that we saw. Okay, good. So then I think I can do a few more examples, and then, yeah, that is, the timing is not even bad. So here we do example. For n greater or equal 0, we're going to look at the Hilb 1, so of Pn over Z. Okay? So we go again, and 1 means the constant polynomial 1. Now what variety has, now I'm parameterizing subschemes of Pn, so over the field. What subvariety of Pn has that Hilbert polynomial? I think only a point can do that, right? The fact that it doesn't depend on how much you twist means that it has dimension 0. If I have more than 1 point, then already my H0 has more, right? If I do 2 points, then I would get a 2. And if I take non-reduced points, I also get more. Now, this is the scheme. Here you are parameterizing points in Pn. And who parameterizes points in Pn? Who represents this? Pn itself. Yeah, so this is Pn, right? That's easy. But now we're going to look a bit higher, right? So Hilb 2 of Pn over Z. So now, do I want to do that? Yeah. So what kind of subschemes over the field do you see here? Right? You see over K, it's K bar, say. You see that you get spec K, disjoint union spec of K. I mean, I have to parameterize subschemes that have are 0-dimensional and as a ring are a K algebra of dimension 2. So there is one other possibility, that is namely you take K epsilon with epsilon squared is 0. This is 2 points, and here you have 1 point with a tangent vector. That is what happens when they have collided, these 2 points. And how do you parameterize those? If you want to embed such a thing into, maybe here now we take n greater or equal 1, okay? Otherwise, this one doesn't, well, even this one doesn't fit injectively. So, yeah, I can tell you that if you have in P1 or P2, or if you have 2 points, then there is a unique line through these 2 points, right? Projective geometry sometimes is simple. So this maps to the Grassmann variety of lines in Pn, right? And that is, I think, n plus 1, 2. Okay? It maps to that. And if I have given a line, how can I parameterize these subschemes? Yeah, also this one gives me a line because it gives me a tangent vector, right? So even in the degenerate case, I still have my image. Huh? And when I have a point here, then what lies over it? Well, that is the number of the possibilities you have on a given line to put such a subscheme. But that we have already looked at. That is degree 2 divisors on this P1, right? So actually, on this you have a universal line, and you should take the symmetric power, the symmetric square of that. Right, so you have also L2 mod S2 here, and this is isomorphic to that. Yeah, it's still easy. But then I point out a more difficult case, so we are going to look at n at least 2, and we do Hilb, or maybe n equals 2. Let's do that. Hilb 3 of P2 over Z. Okay, now we want to do 3 points. And now what can you do? You have 3 points you can have. You can have 2 points. Well, yeah, I should not draw them on the line, right? So 3 points. You can have 2 points with one with a tangent vector. Or you can have something uglier, namely that corresponds to the ring K, X, Y, modulo X squared, X, Y, and Y squared. And this causes now trouble, because this is not a complete intersection in P2. If you want to generate the ideal of this, in the affine plane, for example, where this lies at the origin, you need already 3 generators. Because the ideal is this, and modulo this times the maximum ideal, you see a vector space of dimension 3. And so you cannot, so the codimension is 2 of this scheme in the plane, but you need at least 3 generators. So it's more difficult to parameterize it. And that is, I think I'll illustrate a bit later how that problem gets solved. Okay, so I think it's time for a break.
So do you also have K epsilon modulo epsilon cubed?
Oh, sorry, yeah, you have also this a bit longer, right?
Yeah. Oh.
Yeah. Yeah, you have that too, yeah, sure, yeah. Thank you, yeah. Yeah.
Hans, could you just remind me what the definition of the cross model? I think.
Actually it's a quad scheme. So let me say that, right? In the magic kind of language we have now, we can say, well, this is quad of Z of O to the, well, I want n plus 1 over space Z, over space Z, I think, right? Do I need 3 schemes? For the quad, I needed 3 schemes. Huh? I was X over S, and on X I had something. So I write another spec Z here. And then I should put some Hilbert polynomial. I want quotients that are locally free of rank 2. That is this 2. Because if I take the, so actually the some phi here. Right? But actually I think you can just say twisting on spec Z doesn't do anything, so I'm quite safe to say 2 here. Right? Because if I take over the field, I work over a point, I have a vector space of dimension, I have the vector space k to the n plus 1, and I'm looking at quotients of rank of dimension 2, and those are quotients where the H0 is 2-dimensional and all the higher cohomology is 0 because it's on a point. So that's the 2. Okay, but this is a complicated description.
Okay, it's really something classical. Maybe.
Yeah. It is a really. You could also say this Grassmannian is the same as GL n plus 1 modulo. So actually, if I think of the vector space k to the n plus 1, I have an action of that of GL n plus 1. And if I think of my favorite subspace of dimension 2, I can say, well, the subspace, I have a base point in that variety. It is k times E1 direction, k times E2. That is my standard subspace of dimension 2. And if I let the group act, I get them all the subspaces of dimension 2. So I just have to divide out by the stabilizer of this one, and that is the matrices with blocks. Here I have 0, star, 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 and this is a 2 by 2. Right? And then you can also, you have understanding of that, you can make this into a scheme if you like, and do all that. Yeah? That's more concrete. You can compute the dimension, for example, right? You can do n plus 1 squared minus the dimension of this. You see that you just get the dimension of this block here. So n 2 times n minus 1 in this case. Okay. We had a break, right?
No, we have a break now.
It's a break, yeah.
Sure. So we could even 5 minutes.
Well, or 10.
Or 10, sure.